All right, in this lecture, I'm going to cover the ins and outs of hypothesis testing. This is going to lean heavily on the theoretical and conceptual side because hypothesis testing is a framework of an approach for analysis that applies to any subsequent specific statistical test we can do. So it's a series of steps that is to be applied to any statistical analysis. The idea is to understand how hypothesis testing works. If you kind of understand it on a theoretical level, the idea is that going forward, you're not going to need to spend a ton of time thinking about hypothesis testing if you sort of understand how and why it applies to any analysis that you do. The really basic takeaways I'm hoping you'll glean from this section is essentially just an understanding of p-values and statistical significance. These two concepts get discussed pretty widely when talking about statistical tests, but it's the kind of thing that a lot of people either misunderstand or don't quite understand what specifically p-values mean and what the concept of statistical significance is. So if there's any two most general takeaways you'll hopefully get after hearing this lecture, it's what does a p-value actually represent? Because that value does have a specific probability-based meaning. And p-values are intricately related to this concept of what we call statistical significance. Again, I'll reiterate that this is going to lean heavily on the theoretical side, but the idea is if you can get your head conceptually around what hypothesis testing is, which is a framework for plugging your statistical analyses into certain ideas around probability, you're not going to have to spend a whole ton of time thinking about it going forward, as long as you basically understand how it works. So we started our analyses this semester by doing descriptive statistics, the really basic analyses that let you summarize something going on typically within a single variable, so the mean or the standard deviation. We want to move beyond that basic description of our variables to try and make conclusions about what's going on in terms of our variables being related to one another. The specific question that an inferential statistic will help you answer is going to depend on the kinds of variables you measured and the kind of research design you used. So, if you're doing a correlational analysis and you're just trying to assess whether or not variables are associated, inferential statistics will help you make that conclusion to a measure of certainty. A slightly different question would be whether or not two groups are different, such as two groups having a mean value of some outcome. Are the two groups different from one another? That is, again, the kind of question that can be asked and answered in a framework of inferential statistics. So we're more so going beyond more basically summarizing our data to making inferences about whether or not our variables are associated. So this process of being able to use statistics to make interpretations about the world relies on this hypothesis testing framework. Essentially, hypothesis testing is going to be a series of ideas about the relative likelihood, that is to say probability, of a series of hypothetically possible outcomes. This is going to be a framework where we can specify the predictions that we're making, and we can quantify the likelihood of our being correct or our finding an effect that truly is there. So again, this framework will apply to any subsequent analysis we're doing and any specific research question you have. Again, the specific method that you're using to evaluate your variables and the measurement approach is going to determine what specific statistic applies, but questions like, is there a relationship between exercise and happiness, or what treatment works best for migraines? These are two very different kinds of research questions, but they both work within this realm of inferential statistics and the process of using hypothesis testing to do them. So whether or not your research design is correlational, experimental, it doesn't matter. Hypothesis testing through inferential statistics will work. The basic idea of going through this whole rigmarole of hypothesis testing is partially because our statistical analyses are typically aimed at learning some truth about a broader population, so some group that has at least one characteristic in common. Typically, we can't study an entire population because there's just too many people in that group to assess. So, the solution that statistics and sampling procedures provides for us is the idea that we can merely test a subset of that population to try and draw these inferences about the population from which that sample was derived. So, this is essentially what our statistical analyses are going to be about. We're going to collect data from a smaller sample that's meant to be representative as possible about the population from which they were derived. We're additionally going to be approaching this issue of representativeness and trying to glean truths about populations by using good, solid statistical processes as well. Again, this hypothesis testing framework is essentially a number of ideas about probability that sort of restrict us from making unreasonable or outlandish claims about the population. It's sort of a way that we can make sure any inferences we draw from our sample statistics are appropriate to generalize to the population in general. So, how do you do this? How do you make conclusions about the data? This hypothesis testing approach essentially dictates a series of sequential steps that tries to make sure that we're coming to the best possible quality conclusions. One critical piece of this is to derive our predictions in advance. This is partially what's at the heart of hypothesis testing. The idea being that we want to make our predictions about what we think will happen in advance of actually collecting data and running an analysis. This will somewhat keep us honest. It will keep us from finding fluky results in the data that we didn't predict and going ahead and concluding that it means something. It keeps us specific, it keeps us targeted, and it keeps us from coming to unreasonable conclusions about the data after the fact, or sort of forcing our data to fit a narrative that we created after analysis. Now, hypothesis testing, you want to decide in advance what you think will happen, and you want to stick to that. In order to establish that variables are related, you not only want to establish your prediction in advance, you also want to make some decisions about quantifying the strength of the results you'd need to see before you're willing to conclude that you found a genuine effect and not just an artifact of a fluke. So, not only do you make a prediction about what correlation you're expecting to see, you also want to quantify how strong that correlation needs to be before you're willing to trust its legitimacy. You do the same thing for other non-correlational types of designs, right? If you're trying to establish that two groups are different from one another, let's say you're having two treatment groups, one who's receiving active medication treatment and the other who's receiving a placebo control. You want to make your prediction that you think the treatment group will be better at the end of data collection, but you also want to establish and quantify just how much better the treatment group needs to be to decide that the treatment is legitimately working and makes a true difference. So you want to create these predictions in advance, as I said. So a hypothesis is your prediction. You can use hypothesis and prediction largely interchangeably. So your hypothesis is basically your research prediction about what you expect will happen upon the data being analyzed. This is not meant to come out of thin air. It should be an educated guess about what you predict you'll see based on any sort of background research you've done or prior observations that you've made. The hypothesis should reflect the general research question or problem that you're interested in that drives your interest. It additionally needs to be a prediction statement that can be translated into a research question and a testable research design. In order to create a good quality hypothesis, you should try your best to conform to some basic standards of essentially clear communication and clear writing. One thing is that your hypothesis should be declarative. That means your hypothesis is distinct from your general research question. It is meant to be the prediction statement. So your hypothesis should be a declarative sentence stating what you predict you will find. It should be worded in terms of the relationship that you're trying to uncover between variables. I'll discuss this a little bit more later, but Typically, your hypothesis should not be about trying to find the absence of a relationship between variables, because the logic for trying to demonstrate a negative or an absence of a relationship works a little bit different than trying to find that two variables are related. So, your hypothesis should be structured around what's the relationship between variables you're seeking to find. There should be a theoretical backing to your hypothesis. Basically, again, this should be an educated prediction, so any background research or prior observations should help inform the prediction statement that you create. And additionally, a hypothesis should be brief and to the point, and each hypothesis statement should only say one thing at a time. You can have multiple hypotheses in a single round of data collection and analysis. That's okay. You do want to distinguish each individual hypothesis and make sure that each hypothesis is only saying one thing. A good approach would be to identify your primary hypothesis, the main goal of your research, and then you can have supplementary hypotheses that you'll look into as well. But each hypothesis statement should be concise. And lastly, you do need to make sure that your hypothesis is able to translate into a testable format, however that might be, whether it be a series of self-report scales and surveys or an observational study. Whatever it is, it needs to be something that's empirically testable. So now I'll outline the basic steps at play in your hypothesis testing framework, and I'm going to break these down and sort of beat them into the ground. So first up, you need to construct your hypothesis statement, and that's the first step. So this is when you actually write your prediction statements. I'm going to get into this, but essentially in any inferential statistic framework, you're going to construct two competing prediction statements, and essentially your data collection and analysis are meant to demonstrate which one of the competing hypotheses appear to most accurately reflect what you have found. Again, in advance of data collection and analysis, you need to quantify how strong of an effect you want to see before you're willing to accept that your findings represent a legitimate effect and not just a random fluke. This is again going to happen in advance of the data collection. I'm going to spend a lot of time talking about this step. Ironically, after you get past hypothesis testing conceptually, this is where you can spend the least amount of time when you're actually running an analysis. Once you understand how p-values work, essentially, you can set up your decision rule without even really thinking about it or explicating it, because we all sort of, in the psychology field, share a status quo for what decision rule we're all using. But it is important to understand theoretically what's happening at this step. The third step in the process, which I'm going to spend essentially no time talking about today, is the actual collection of data and the data analysis. In all the subsequent lectures, we're going to be spending all our time learning about different analyses we can run at this step. And this is sort of the bulk of what any statistics class will do, is just show you different test statistics that you can run for different kinds of data and different kinds of variables. But I'm going to spend the least amount of time on that today because, like I said, all subsequent lectures will be devoted to learning the different statistics that can get plugged in at this step. Then, once you actually run your analyses, you have to apply the decision rule and interpret. Essentially, you ask yourself whether or not your prediction was borne out by the data analysis and whether or not you cleared the decision rule that you set for yourself in step 2. And then at that point, you can interpret what it is you actually found and what your analysis basically tells you. And again, this basic process undergirds all of the subsequent statistical tests we're going to do. The remainder of the semester will be adding different tools to your toolbox of different statistical analyses, but it's important to understand hypothesis testing because this framework will be in place for all of the analyses we do from here on out. So let's start with an example to walk you through hypothesis testing with as basic a hypothetical as possible. I'm going to use an example that relies on simple probability like you learned about from the previous lecture on calculating and computing probability. This will hopefully help illustrate that all of hypothesis testing sort of relies on principles of probability and trying to figure out relative likelihood of various hypothetically possible events. So, like I said, I'm going to keep it very, very basic for demonstrating hypothesis testing because when this process is applied to subsequent analyses, it's going to get a little more complicated. So, to get our conceptual knowledge of hypothesis testing down, let's start with a really basic example. Let's say we have a coin that we think might be biased. We think this coin might not be fair, based maybe on previous observations of coin flips. We start to suspect that the coin is biased towards heads. We don't just want to sort of take our gut reaction, we actually want to subject this to some rigorous testing. So what we would do in this case is perform a series of tests to determine if the coin is fair. We're going to be able to use this basic example to walk through all 5 steps of the hypothesis testing approach. So number 1, construct your hypotheses. As I mentioned, in any research study, you should construct 2 competing hypotheses that will essentially compete head to head to explain the results you eventually will be analyzing. The first is what we call the alternative hypothesis, also known as the research hypothesis. You can use the 2 terms interchangeably. I often will notate this with that H sub A notation, so if you ever see that, know that that stands in for the alternative hypothesis, but you can refer to it as the research hypothesis if you like. So this is basically the research statement that reflects what it is you're predicting that you will find, what you're hoping your data analysis will demonstrate. So if my suspicion is that the coin is biased towards heads, I need to think about what that means in terms of what I'm predicting. In this case, it might be a prediction statement such as the probability of a coin landing on heads is greater than 50%. But this process of creating an alternative hypothesis will apply to any sort of research question you have, as long as it's framed in terms of the relationship between variables that you're trying to find. You should typically think of your alternative hypothesis as the relationship between variables that you are hoping to find. The reason is because you don't typically want to go about searching for a lack of a relationship between variables. The reason is that it's logically harder to prove a negative. If you're familiar with the phrase, absence of evidence is not evidence of absence. So just because you fail to find a relationship between variables in your particular research analysis does not prove that those variables are unrelated. It just proves that you didn't find that relationship there. Proving a negative takes a lot more collections of data to try and set up a precedent for the variables being unrelated. So scientific research is typically not geared towards not finding something. So typically you're going to want your alternative hypothesis to be what you are hoping to find. There are some exceptions to this. One major example would be research demonstrating that vaccines are not associated with autism. There's a vast body of research that has found that there is no relationship between the MMR vaccine schedule and autism. That research is quite consistent, and there's now hundreds of published instances of research demonstrating that lack of a relationship. That's a bit of a special case because that is definitely an endeavor where scientific research is trying to undo a misconception about variables that appear to be completely unrelated, whereas there's at least a certain crowd out there that holds strong to the idea that those variables are related. So that's a bit of a unique case. The vast majority of the time, scientific research is going to be about finding affirmative evidence of something that does exist. So you might reframe the question in the research on vaccines that the research finds that there is a link between vaccines and safety, perhaps. So again, this is not a hard and fast rule, but typically you want to think of your alternative hypothesis as the relationship between variables you're hoping to uncover. The distinction between directional versus non-directional comes into play when you're first crafting your alternative hypothesis statement. Essentially, you've got 2 different options for types of alternative hypotheses you want to create. Directional is when you indicate that you expect your effect in a certain direction or at a certain level. So, for example, if you're doing a correlational study, this would be you predicting that the correlation will either be positive or negative. So, the prediction statement would have language indicating which direction you're predicting. So, eating oatmeal lowers cholesterol. That's positing a negative relationship. This can additionally apply to other sorts of predictions outside of correlations. So, stress heightens risk of cardiovascular disease. Again, the language heightens, exacerbates, worsens, diminishes. These are all words that indicate directionality, and they're a little bit more specific. You can hedge your bets if you don't have a specific direction that you're predicting your variables will be related in. And you can go non-directional. This is when your statement reflects that you would be happy finding a positive or negative correlation, or that two groups will just be different, but you don't know which one will be higher. So, two examples of non-directional prediction statements. You might say living on campus affects GPA. You might be thinking to yourself, well, living on campus could be positively associated with GPA because you're closer to your school class buildings, you're closer to the library. Or you might think that living on campus will be associated with decreased GPA because you're closer to your friends and you might be going out partying more often. So if you have two variables that you have reason to think are related, but you sort of want to hedge your bets and be able to accept a effect in either direction, you might craft a non-directional approach. It's going to be a bit more open-ended and a bit more exploratory. Once you make your alternative prediction statement and you decide to go directional or non, you're kind of locked into that decision at this stage. And this will have an implication for your statistical analyses later on in the process. So do make this choice thoughtfully because it will have an implication for your ability to find statistical significance. Okay, so in this case, let's say our alternative hypothesis is that our coin is biased towards heads. In this case, you can think about the distinction between a directional or a non-directional hypothesis. In this case, if I'm saying the probability of heads is greater than 50% on any given coin flip, that's indicating directionality. If I was to say I want to hedge my bets, I think the coin is biased but not willing to state if it's towards heads or tails, I could instead create a non-directional version of this hypothesis. I'm going to go through this example largely focusing on this directional prediction, but I will show you how non-directional versus directional will have an implication for significance testing later on. So the competing hypothesis that's being pitted head-to-head against the alternative hypothesis is your null hypothesis. This is meant to be the logical counterpart to the alternative hypothesis. This is basically the prediction statement that covers what would happen if we were wrong and our alternative hypothesis doesn't come true. So this is basically a prediction statement that is worded in terms of not finding an effect. When I say the null and the alternative hypothesis are logical counterpoints, what this means is that together, these two prediction statements cover all possible logical realities. So either the coin is biased or it's not, and I want to craft an alternative and null hypothesis set that covers all of those possibilities. Additionally, them being logical counterparts means that one of them has to be true and both of them cannot be true at the same time. One of them will need to end up being borne out as appearing true on the strength of the data analysis. So in this case, if we craft our null hypothesis to be a counterpart to the alternative, we'll say that our coin is not biased towards heads. So the probability of getting heads on any given trial is not greater than 50%. So our null hypothesis covers all of the possibilities outside of what the alternative covered. Basically, this null hypothesis covers a coin that does have a 50-50 probability and anything that is not biased towards heads. Again, the null hypothesis statement is not what you're trying to find, it's essentially what you're trying to find evidence to contradict. But you want to craft this null hypothesis statement so you basically know what you're trying to find evidence in the contrary of. As I mentioned, the alternative and null hypothesis are logical counterparts. So to reiterate that point, they need to be mutually exclusive, meaning that one cannot be true while the other is true. They cannot simultaneously be true, so only one can be true. And additionally, they must be what we call exhaustive, meaning that the two of them together cover all possible hypothetical outcomes. So, in this case, the coin is either biased or it's not. So, the null and alternative hypothesis covers all of those logical possibilities. You should typically seek to word your hypothesis statement in terms of the general population parameters that you're trying to make inferences about. So again, when we calculate our sample statistics, we're hoping to find results that are strong enough that we think they're going to be generalizable to the population. Again, we can employ statistical procedures to try and reduce the hastiness of our generalizations, but sampling is also important. Thinking about whether or not the people who were in your sample were biased in some way, meaning they're not necessarily reflective entirely of the population from which they came. An example of this would be, let's say you're interested in people in general. Let's say you're interested in people from the United States. In the process of data collection, you only manage to survey people who are college students. That's not necessarily a sample that's going to be wholly representative of all people in the United States. There might be something distinct about college students where it's sort of hard to make a generalization about people in general if your sample is just comprised of college students. So it's a valuable thing to keep in mind, even as we're crunching the numbers, that we can't forget about who is actually being reflected in our analysis. Additionally, the hypotheses should be able to be notated using mathematical notation. So you can take your statements and you can translate them into specifically what the numerical outcomes you're hoping for are. So in this case of this basic coin flip example, we're just dealing with probabilities. So our alternative hypothesis is that the probability of getting heads is greater than 50%. The notation for the null hypothesis should again cover all logical possible realities outside of the alternative hypothesis. So whereas the alternative hypothesis is that the probability of heads is greater than 50%, the null hypothesis should be the probability of getting heads is at or less than 50%. So notice that greater than and less than or equal to, those two bits of notation make sure that we're covering all possible outcomes. You can do this process no matter what analysis you're doing. So if, for example, you're doing a correlational study, we're going to end up computing what we call R values, or Pearson's R coefficients. Pearson's R values can be positive or negative. The positive or negative sign of a Pearson's R indicates whether there's a positive or a negative relationship between the variables. So again, you can use this same notation framework. And if you're doing a correlational study, you just need to change a little bit what's written into your notation. So if you're predicting a negative relationship between variables, you want to specifically notate your alternative hypothesis as you predicting that you will get an R that is greater than 0. Less than 0, sorry. So one thing that's important, and part of the reason why we craft a null hypothesis, is that we always want to start with the assumption that the null hypothesis is true, and the burden must be on us to perform analyses that attempt to negate the veracity of the null hypothesis. Basically, until you have evidence supporting that you have found a relationship between variables, you want to assume that there's nothing there, and you want to wait for the evidence to help you confirm the alternative hypothesis. So in this case, we need to start from the assumption that the coin is fair, and we want to perform tests that show that the likelihood of the coin being fair is so vanishingly slim that we have evidence that the more likely conclusion is that the coin is unfair. but the burden is going to be on us to affirmatively provide that evidence. The same thing happens when you do psychological research or you're doing research on treatments. The idea is at baseline, you don't want to assume that a given treatment is effective. You want to start by assuming it's not and put the burden on yourself to show strong enough evidence that it does work. Finally, on to step 2. Like I said, I'm going to spend a lot of time talking through what theoretically is happening at this step, but do keep in mind that once you go forward from this lecture, you're going to be able to basically take this step for granted. As long as you sort of know what's happening at this step and you at least think to yourself that you've spent the time conceptualizing your decision rule, you don't need to spend any time in your analysis really doing anything with this step. Okay? So in order to accomplish the decision rule step is you need to decide in advance of your data collection and analysis what the burden of proof is for accepting the null hypothesis. This is essentially a quantification of just how strong, in a numerical sense, your analyses and outcomes need to be before you're willing to accept that you've legitimately found evidence for your claim. So the way we do this is again by starting off from the assumption that the null hypothesis is true, and we want to proceed from there. Essentially, we ask ourselves, if the null hypothesis were true, what's the likelihood of the result that we get happening by chance alone? So again, theoretically at this step, we haven't actually run any trials yet, but let's say, hypothetically, we know we're going to flip the coin 18 times. Theoretically, if we get 14 heads there, we want to understand just how unlikely that outcome was and whether or not getting that 14 heads out of 18 coin flips is so unlikely to happen by chance that we're willing to go with the alternative explanation that the coin is biased. So this comparison of evaluating the likelihood of our outcome against the likelihood of it happening by chance is going to be constituted by what we call the null distribution. Essentially, when we do hypothesis testing to test for statistical significance, we're comparing our results to an underlying probability distribution that reflects the null effect. We're going to compare our actual obtained results against that null distribution to figure out whether or not our results appear to jibe with the null distribution, or if our results are so unlikely to happen in the null distribution, probability distribution, that the more likely conclusion is that we've truly found an effect. So think of it this way. We're essentially at this point going to be saying, what is the odds that some difference that we found or some relationship between variables that we found was due purely to chance? So to illustrate what this means, let's say, for example, I'm holding a review session on exam performance and I take the mean level of exam grades on people who didn't go to my review session versus who did. On the strength of this evidence, let's say I conclude that those who went to the review did significantly better. I say, look, people who went to the review had a higher mean grade than those who didn't. You might be thinking that I'm being a little bit hasty in my conclusion. You might say to yourself, Christina, a difference of 1 point on a 100-point exam could reasonably happen by chance. Either your review is genuinely only raising grades by 1 single point, or this is just a fluke. The odds of getting a fluky 1-point difference, pretty high. I would say on the strength of this evidence, more likely there's not a real difference between those who went to the review and those who didn't. So what we're essentially going to be doing at step 2 is we're going to be quantifying just how much of a difference we'd want to see before we'd be willing to accept that a effect, a difference, a correlation is legitimate. So going back to our coin flip example, maybe we flip our coin, we get heads 14 times on 18 coin flips and we conclude that it's biased. You might be thinking to yourself, that's a pretty reasonable conclusion. That's not going to happen every day. Yes, that's true, but it's still theoretically possible. Of course, it's theoretically possible to get 14 heads on 18 coin flips. Could be that it's a fluke. Could just be, as my man Fred Durst said, just one of those days. It's okay that there's no such thing as being able to completely rule out the possibility that our results are just a random fluke. Even the strongest of results, there's always a chance that it was just a fluke. But we can't proceed without saying that we need to have a certain cutoff for just how strong evidence needs to be before we're willing to say, okay, the odds of being a fluke is low enough that I'm okay proceeding with saying I have found an effect. So this is your decision rule. This is you setting a standard, a quantified standard, here at step 2, before data collection and analysis, for what percentage chance of getting a fluke you're willing to accept before pulling the trigger and saying you found an effect. So you're going to want to keep this percentage pretty low. You don't want to run too much of a risk that you'll be calling a fluky result legitimate. So you're going to want to be thoughtful about where you set this decision rule, because this is essentially your margin for error of just how much of a chance you're willing to take that you make a mistake. Okay, so the question is, how unlikely does a result have to be before we'd be willing to reject the null hypothesis? We're going to quantify this in probability terms with what we call a critical probability value, also known as our alpha level. This is not the same as our Cronbach's alpha. Alpha just pops up all the time in statistics. If you see in the context of significance testing an alpha level, it likely stands in for your critical probability value. This is going to be the standard that you set for yourself of the chance you'd be willing to take of coming to a mistaken conclusion should you declare you have found an effect. So essentially, what you're going to want to do is figure out a certain probability value that you want to make it to in terms of how unlikely a result has to be before you're willing to throw out the null hypothesis. You're essentially going to want results that are strong enough that they make it past your critical probability value. You want results that are so unlikely to happen by chance alone that it makes it past this critical cutoff, and it will be at this point that you declare statistical significance. So you're going to set your critical probability value wherever you want to set it. This is going to represent a threshold for how small of a chance you're willing to take that you'll be making a mistake should you declare that you have rejected the null hypothesis. So this is the heart of statistical significance. Statistical significance is not about the importance or novelty of your research findings. It's about whether or not your results make it past your critical probability value. We declare statistical significance when our results make it past whatever critical probability or alpha level we set for ourselves. Okay? If our obtained probability of whatever outcome we get is greater than that critical probability value, the idea is we think, well, the odds of our result having happened by chance is higher than I'm comfortable with. So I'm not going to reject the null hypothesis. This is the very disappointing outcome that is all too common in research, where you declare that your results are not statistically significant. I often shorthand this as NS. So essentially, if you calculate your analysis, you run the numbers, and you don't make it past that threshold you set for yourself, you have to be willing to say, looks like I have nothing to see here. Looks like my results have not yielded what I wanted. Do be careful around your language at this point. Don't say that you accept the null hypothesis. As I mentioned, proving a negative takes more than failing to find a relationship one time. You would need to demonstrate the absence of a relationship many more times than just in a single analysis to accept that variables are unrelated. So say instead that you failed to reject it. So you don't want to say that you've proved the null hypothesis, just that you failed to reject it at this time. So as I mentioned, despite the fact that I'm talking nonstop about this decision rule step, this is where p equals 0.05 comes in. Typically, sort of field-wide, in psychology, we accept a critical probability value of p equals 0.05 as our bare minimum critical probability cutoff. So when I say you don't actually have to spend a lot of time thinking about this step, basically, you should just run with p equals 0.05. Unless you have a reason to be more conservative and have a smaller decision rule, you can just go with p equals 0.05. That's the decision rule that's programmed into SPSS. That's the decision rule that we sort of all accept as the bare minimum in the field. So when I say you don't have to really think about the decision rule, essentially, unless otherwise stated, you're just going to be using alpha, or p, equals 0.05. What this means in specific probability terms is that we're willing to accept at a minimum, or at a maximum rather, a 5% chance that we'll be making an error should we state we're willing to reject the null hypothesis. So we want results that are 5% or less likely to happen on the basis of chance alone. So, as I mentioned, p equals 0.05 is sort of a field-wide standard. There's lots of scientific fields that sort of share this sort of baseline status quo decision rule. What this means, though, is if you're talking about a body of research that's all using this same p equals 0.05 critical probability cutoff, that means that any particular research study has a 5% chance of being mistaken. Otherwise stated, there's likely 5% of published research out there that's completely wrong. So at this point, you're allowed to sort of think critically about whether you're okay with this. Is a 5% chance of being wrong, or 5% of the literature out there being wrong, too much or too little? You're allowed to think critically about whether or not you buy this. You might be thinking, is that too much? Is that too much error? Well, it kind of depends on, I guess, the stakes of the research that you're doing. If you're talking about social psychology research, you might be thinking, so what if 5% of the research out there is bunk? I would say that you still want to think critically, even if it feels like social psychology is not life and death, whether or not you're comfortable with that 5% error rate. For example, social psychology does research on things like racism and prejudice and discrimination. So we are studying some heavy topics there. Psychology has the entire field of clinical psych, so actually helping people treat their mental illness and understanding mental illness. So again, these are some somewhat high stakes sorts of areas of research. Additionally, think about it this way. There's certainly aspects of life where you'd be very, very uncomfortable taking a 5% chance of being wrong. Let's say you're going to ride a roller coaster and you hear that there's a 5% chance that you're going to get your head cut off. Probably no one's going to ride that roller coaster. So you really have to step back and put things into sort of concrete human terms. You're allowed to think critically about whether or not you think a p equals 0.05 is too much. On the flip side, you would have a ability to compellingly state that you think it's actually too little. If we are only accepting results that meet this pretty stringent 5% cutoff, we might be throwing out lots of perfectly legitimate research just because it didn't meet this arbitrary 5% cutoff. What if you have a p-value that's 0.06 or 0.07? Essentially, if we're locked into this hypothesis testing framework, we'd be forced to say, sorry, too bad, that's not statistically significant, throw it out, start over. What you're doing by setting P at this 0.05 level is you're basically going along with the field standard where we think that it's not too much. 5% error rate is basically not letting a lot of fluky bad research in, but it's also not sort of prohibitively small. If we were to set that p-value even smaller, we just might be throwing out lots of legitimately good research that finds effects because it doesn't meet our sort of unreasonably small probability cutoff. So all of this is to say a couple things. A, you can use p equals 0.05 and spend not much more time thinking about what goes on at the decision rule stage. But B, I would encourage you to use a little bit of critical thinking. Do you think this is an appropriate cutoff? Do you think it should be adjusted? Are you comfortable with this? Okay, so on the same topic about decisions, the hypothesis testing framework provides us the ability to map out logically all the possible outcomes that might occur upon our data analysis. So if we think about the logical parameters we've set for ourselves, we're going to end up making a decision one way or the other, whether or not we've found evidence for the alternative hypothesis or whether or not it appears that the null hypothesis appears more accurate. So we might make a decision that there is a relationship between variables because we have support for the alternative, or we might conclude that there's not a relationship between variables because unfortunately we didn't get statistical significance. Our ability to discover truth notwithstanding, the idea is the truth out there could also be one of two things. The truth could be that there is a relationship between the variables or that there's not. Again, we've set up the logical parameters such that it has to be one thing or the other. So this sets us up for a world in which we have 4 possible outcomes. We can be right. Whether we conclude there's a relationship or not, we could be right. We always prefer to be right as opposed to wrong. But we could also be wrong in 2 distinct ways. We don't like being wrong, so we want to spend some time thinking about how to quantify our error rate and the different kinds of errors we could make. When applying our decision rule, we're basically locked into a logical reality where we can make 2 distinct types of errors. This is, I'm sure you've heard of type 1 and type 2 errors. This just refers to the fact that there's 2 possible kinds of mistakes we could make when we're using this inferential statistics process. Your type 1 error is when we decide to reject the null when it's actually true. Otherwise stated, a false positive. So we really don't like making type 1 errors. When we declare that we've found an effect but we're wrong, that's pretty bad. That's like we get something published and then we have to retract it later, level bad. We really want to minimize the likelihood that we're going to make this particular kind of error because it's got a little bit higher stakes to be wrong in this direction. A distinct type of error that's still not great, we still want to minimize the likelihood that we'll make this particular error, is when we decide to retain the null when it's actually false, so false negative. This is when, for whatever reason in our data analysis, we did not find statistical significance, but it was only because of our failure to do so. Maybe an insufficient sample size, maybe our approach to analysis was wrong. False negative is when you conclude that you haven't found a relationship, but there actually is one out there that you failed to uncover. If you want a tip for remembering which one is type 1 and which one is type 2, one tip I heard years ago was that if you take type 2 and you just draw a little line connecting them from here to here, it turns into an N for false negative. Maybe that helps one of you, maybe it helps none of you, but it helped me. So this quadrant basically maps out all of the possible outcomes that could result from our hypothesis testing framework. We could be living in one of these correct decision quadrants, where essentially we have made a correct decision whether or not we have found an effect. So this quadrant here is when we've made a correct decision to retain the null. We have correctly identified that there's no relationship between variables. This quadrant, on the other hand, is our making a correct decision about there not being an effect. Oh, sorry. This quadrant is when we've made a correct decision about there is an effect. So we would prefer to be in one of these two correct decision quadrants. Obviously, it's most ideal to live in this correct decision where we have found an effect. We like that the best, but it's always better to be right than to be wrong. Then you've got these two quadrants representing your errors. So the type 1 error, again, is your false positive, which we very much want to avoid. Your type 2 error, your false negative, again, we don't like that either, but perhaps it's a little bit less of a dire mistake. So what these quadrants depict are the 4 possible, hypothetically logical outcomes that we could come to upon our data analysis ending. Additionally, we can quantify the probability of landing in any one of these quadrants. For example, type 1 error is alpha. The reason p-values and alpha can be used interchangeably is because our p-values are stated in terms of the type 1 error rate. Since we're most motivated to avoid a type 1 error, we put our critical probability value into terms of type 1 error rate. Okay? So our likelihood of making a false positive conclusion is going to be defined as alpha. So your type 1 error rate or your false positive error rate is going to be quantified with a probability value notated as alpha. The type 2 error rate additionally can be quantified with its own notation. I believe this is a beta. If you ever see beta in the context of hypothesis testing, this is the quantification of the probability that you make a false negative. This quadrant is an interesting one. You're not going to have to compute this, but it is a concept that you might read about if you're ever reading a paper that contains significance testing. Your probability of being able to find an effect, if it's truly there, is termed what we call statistical power. We are somewhat uniquely interested in this concept of statistical power because there are certain things we can do to raise the statistical power rate, for example, by having a sufficient sample size. Essentially, there are things within our control as researchers and analysts to make sure that if there truly is an effect out there, we're going to be able to find it. So basically what this quadrant represents is a depiction of all of the possible outcomes, and it's a way to quantify the probability of landing in any one of them. Okay, so again, p-values are typically your type 1 error rate, which is why you often see them used interchangeably with alpha. But you could also have p-values that are depicting your type 2 error rate, and they would be notated as beta. There's a trade-off between your type 1 and your type 2 error rate. Essentially, you're going to set your critical probability value wherever you set it. What that means is that you're sort of locked in to being at one particular critical probability value, and you have to accept that you've got sort of a room for error in the other direction. Essentially, if you were to decrease your alpha rate, your type 1 error rate, let's say you think p equals 0.05 is too high, so you say, screw it, I'm going to be really strict and I'm going to set my alpha at 0.01. I'm only willing to accept a 1% chance that I've made a mistake. What you're going to see is a trade-off where that type 2 error rate probability is going to go up. Essentially, you're going to be throwing out a whole bunch of possibly legitimate effects at p equals 0.02, p equals 0.03, and p equals 0.04, and p equals 0.05. What you do by setting that type 1 error rate at a stricter cutoff is you're making more room for the other type of error. So this another reason why there's just sort of a field-wide status quo for p equals 0.05. The idea is there's this fundamental trade-off, and p equals 0.05 is seen as sort of a sweet spot where the type 1 error is low enough that we feel that we're not likely to make a mistake, but we're not introducing too much of that type 2 error rate. We want to be able to find effects that are there. And we're going to be able to do other things to minimize the probability of making a type 1 error. Again, things in our control as researchers, like having a sufficient sample size or replicating our own research. There's ways that we can try and minimize this type 1 error rate, which is, again, one of the primary motivations for this entire rigmarole. All right, finally on to step 3. Now we're moving somewhere. As I mentioned, we're not going to spend a lot of time in this lecture lingering at this step because this is where you actually collect and analyze your data. And this is where we're going to be living for the remainder of the semester. And this is really where you spend most of your time and attention learning about statistics, is what analysis should I do and how do I do it? Like I said, that's a question for future lectures. In this case, in the hypothetical we've been using, the data that we collect, hypothetically, is going to be the number of heads we got on 18 coin flips. But this process, again, can be plugged into any analysis that you do. So you might run your Pearson's R correlation, you might run your analysis of variance, you run your chi-square. Again, it feels like we spend all our time at this step as statisticians, which is fine. Just make sure that you know that this whole probability-based framework is happening kind of underneath the hood when you're doing any analysis. So next, we're going to have to determine the probability of obtaining the outcome that we get if we assume the null distribution is true. So again, we're still operating under the assumption that the null hypothesis is true, and we have to compare our obtained outcome to the null distribution. So for this, we're just going to be using a binomial probability distribution because coin flips are an example of binomial probability. But for future research, there's going to be a unique null distribution for your Pearson's R, for your ANOVA, so on and so forth. All right, so application of the decision rule. We're finally making some moves. Here's what we need to know to accomplish this step. We need to know our critical probability value. If it's p equals 0.05, that's fine. We need to evaluate the probability of getting our obtained statistical outcome. So in this case, let's say we got 14 heads on 18 coin flips. We need to know the probabilities as defined by the null distribution. And we need to compare our obtained statistic to this null probability distribution. This probability distribution on the right just depicts the likelihood of getting any theoretical number of heads on 18 coin flips. We're not doing binomial probability this semester, so you don't need to trip too hard on understanding how I got this probability distribution. Every statistical analysis is going to have a unique null distribution associated with it. So here's what goes on in this step. The idea is that some obtained statistical outcomes are going to be so extreme that they're unlikely to have come from the null distribution. Even though a result might theoretically possibly be a fluke, if it's so extreme that it's just really, really unlikely, at that point we can likely say to ourselves the null distribution doesn't appear to adequately capture what we found. Specifically, in evaluating whether or not our scores are extreme enough, what we're going to do is identify an area of the null distribution called the region of rejection. The region of rejection is going to represent a portion of the null distribution that's extreme enough that it causes us to reject the null hypothesis. Again, the idea is an extreme score, although theoretically possible to come from the null distribution, i.e. to happen by chance, if it's extreme or unlikely enough to get us into this defined region of rejection. Yes, it is possible that our results were a fluke and just happened by chance, but more compelling of an explanation is that the null distribution is just not true. Okay, so revisiting our example, our hypothesis was that the coin was biased in favor of heads. At this point, directional and non-directional predictions come back into play because this is going to actually somewhat shape how we apply the decision rule. If we're dealing with a directional hypothesis, we're only willing to reject the null hypothesis if there are more heads than we would expect by chance. Essentially, what this means is we're only going to look at one tail of the null distribution to evaluate whether or not we've achieved significance. If we set our p-value to p equals 0.05, then we say to ourselves, if our obtained result is in the upper 5% of the null distribution, we are saying that our result is so extremely unlikely to happen by chance, i.e., it's only going to happen by chance 5% of the time or less. At that point, we will be able to say we reject the null hypothesis. So again, we want results that are compelling enough or extreme enough that they've made it into this very extreme region of the null distribution. So how do we figure out if our score is in the region of rejection? We basically ask ourselves what percentage of scores are at least as extreme as the obtained scores, but only on the one tail of the null distribution. Okay? If that probability of our outcome is greater than that critical probability value we set in advance, basically we have to conclude that our results are not more extreme than expected by chance, and we cannot reject the null hypothesis. But if we make it to and past that critical probability value, that is to say, if that probability is more extreme than expected by chance, then we can reject the null hypothesis. So this directional hypothesis, if you make a directional hypothesis in advance, you are essentially opening the door to doing what we call a one-tailed test, because you're going to evaluate a region of rejection that only exists on one tail of the null distribution. A non-directional hypothesis, on the other hand, would lend itself to what we call a two-tailed test. That's because if you made a non-directional prediction, you want to open the door to finding an effect at either end of the probability distribution tail. So what you do is you take that same region of rejection and you split it in half and you plop one on one tail and the other on the other tail of the null distribution. That leads us to what we call a two-tailed test because it's captured by two-tailed probabilities. So if we were to tweak our coin flip example and go non-directional, we think the coin might be biased towards heads or tails. Essentially, we've changed our approach for our hypothesis, and we would need to change our approach for our significance testing. In this case, if we wanted to open the door to reject the null hypothesis with either more or fewer heads than expected by chance, like I said, you want to keep that region of rejection consistent. So, if you have a critical probability value of p equals 0.05, you take that 5%, you split it in half, and you plop one on the upper half of the distribution and the other on the lower half of the distribution. So what you're doing is you're actually making the bar for significance further out into the extreme. You're actually going to need to get a score that's only going to happen 2.5% of the time or less. But you're going to have a region of rejection on both tails of the distribution. Okay, so to depict this in a way that hopefully makes it make a little bit more sense and be less abstract, if you're dealing with a one-tailed test, you create for yourself a one-tailed region of rejection, meaning that in order to get a significant result, you need to make it into that upper 5% of the tail. Okay, so you see there, the result that will happen 5% of the time or less is to get 13 heads on 18 coin flips. We would need to have a result more extreme than that to make it into the region of rejection and declare statistical significance. So this appears to be a bigger region of rejection, but that's because we only have one on one side. A two-tailed region of rejection, on the other hand, keeps that critical probability value consistent, but divides it in half so that there's a chunk at the high end of the distribution and the low end of the distribution. So see how that bar for achieving significance has been moved further out into the extreme? You need to make it to a more extreme result in order to achieve significance, but you have a region on the extreme towards head side and the extreme towards tails side. So you see that that bar for significance is a little bit more extreme. You would need 14 heads on 18 coin flips to achieve that 2.5% region of rejection. But if you also found an effect where you had 4 heads on 18 coin flips, so the extreme opposite end, on the very other end of the spectrum, you could make it into a region rejection down there as well. So essentially, by making a directional prediction, you're creating a region of rejection that's chunked on just one tail of the distribution. But if you want to hedge your bets and go non-directional, you're going to need to split your region of rejection in half such that you have one region on the high end and the other on the low end of the distribution. So technically, these regions appear smaller. It appears that you need stronger or more extreme effects to achieve significance, but you've opened the door to find an effect on either direction. One thing that's important to keep in mind, one-tailed tests on a certain level are easier to achieve significance. It shouldn't be in practice, but if you were to initially use a two-tailed test and not achieve significance, and then flip to one-tailed, you might notice that your actual obtained p-value was lower than it was with the two-tailed test. Since the bar for reaching significance is technically not as extreme with a one-tailed test, it is in a certain manner easier to achieve significance. You need to have a specific prediction in advance that merits the use of a one-tailed test. You need to make a directional prediction in advance to ethically be able to use a one-tailed test. Additionally, you need to keep yourself honest and hold yourself to the standards of the one-tailed test. The reason one versus two-tailed tests are both able to keep that critical probability value consistent is that if you use a one-tailed test, technically you should not accept as significant results on the opposite end of the spectrum where you did not predict to find results that would support your alternative hypothesis. So if you had used the one-tailed test, the idea is if, let's say, you found that you only got 4 heads on 18 coin flips, despite the fact that that was compellingly extreme in the opposite direction, you'd be forced to say, sorry, that didn't meet my prediction, not significant. So you're sort of locking yourself into one direction. With the two-tailed test, you do need to meet a more stringent cutoff to achieve significance, but you're opening the door to find an effect in either direction. So in order to keep things consistent and ethical, your choice of one-tailed versus two-tailed test should be married to whether or not you made a directional or non-directional prediction in advance. You can always save yourself the headache and just err on the side of using two-tailed. Honestly, even if you made a directional prediction, you could go ahead and use two-tailed and it would be fine. Two-tailed tests, given that they're a slightly more conservative or extreme cutoff for significance, it sort of never hurts to make the bar a little higher for yourself to clear. So if you're ever wondering, should I use one-tailed or two-tailed, and you sort of don't know what to do, just err on the side of two-tailed. You'll never go wrong using two-tailed. If you choose one-tailed and you didn't have a reason to do so, then that's kind of problematic. Okay, so in terms of applying the decision rule, again, we're not learning about binomial probability this semester, so you don't need to trip too hard on that. But essentially, I put together the region of rejection for this particular example, and I calculated the probability of getting 14 heads on 18 coin flips or any more extreme results to altogether put together the chance of getting 14 or more heads on 18 coin flips. This 1.55% chance of throwing those 14 heads in 18 coin flips There's a couple things to note about that. One is that that's a real probability that represents the real chance of getting that outcome, right? That's only going to happen 1.5% of the time. It's quite extreme. That p-value is less than 5%, so we have made it past that critical probability cutoff. So one thing I'll mention at this point is that no matter what your critical probability cutoff is, the specific p-value associated with your outcome is going to meaningfully have to do with the probability of getting your specific obtained outcome. So to assess for statistical significance, the only important question is whether or not it's lower than p equals 0.05 or 5%. The specific p-value associated with your outcome beyond that is a meaningful probability in and of itself. So p-value is a probability value. For any analysis that you do, you're going to have an obtained statistic, in this case, 14 heads, and you're going to have a p-value. You're going to get an obtained statistic, and it's going to have its own p-value. Okay? So just making it past p equals 0.05 is one thing, but the specific p-value itself is additionally informative. All right, so finally, we're seeing the light at the end of the tunnel. We need to interpret our results. Basically, did we make it past p equals 0.05? We're going to compare our obtained statistical value to the region of rejection. Again, we compare our obtained statistical outcome to the critical probability value. So in this case, we're dealing with probabilities. So did our outcome make it past 5% likelihood of happening? In this case, yes. 14 heads on 18 coin flips is only going to happen 1.5% of the time, which is even less likely than 5%. So if we chose p equals 0.05 as our decision rule, this result gets us into the region of rejection, meaning we can reject the null hypothesis and we can accept the alternative, meaning we have affirmative evidence that the coin is biased towards heads. We win. Okay? So our critical probability value is going to be wherever it is. This is not going to move around. It's right there at that spot in the probability distribution. We're just going to compare whether or not we made it past there. We need a result that gets at least to this line and hopefully past it. Well, this is where our outcome actually is. What that means is that we have A, made it into the region of rejection, B, we have attained statistical significance, and C, P is less than P equals 0.05. So all of these things are interconnected. Okay? If we had used a two-tailed test, for hypothetical sake, if we had split our region of rejection in two and created two distinct regions of rejections, even using two-tailed, our obtained outcome is not going to change, and it still makes it past that even more stringent, that even higher bar for significance. It even makes it past the two-tailed critical probability value of p equals 0.025. So in this case, the distinction between one-tailed and two-tailed test doesn't actually make a difference in terms of our decision to declare statistical significance. Every once in a while, it will. If, let's say, you had a p-value with your obtained outcome of p equals 0.04, you're right in between, you're right in that space where you'd be significant with one-tailed but not with two-tailed. Every once in a while, this distinction is going to be the difference between significance and non-significance. But this hypothetical demonstrates a sort of a ideal outcome where it doesn't matter. Both with a two-tailed and a one-tailed test, we got statistical significance, so we can feel pretty confident that these results are legit. Now, if the obtained probability, that is to say the p-value associated with your obtained outcome, is greater than p equals 0.05, that means you have not made it into the region of rejection. There's a greater than 5% chance that your result could have been a fluke. So we feel less confident that we have support for the alternative hypothesis. That means we failed to reject the null hypothesis. We have failed to achieve statistical significance, NS. Okay, so that's not what we found here. But any time in your analysis your p-value is greater than 0.05, that means your results are not statistically significant. We don't like that. It happens a lot. Get ready for disappointment. It happens all the time, but that's what that means. Okay, so if you want to prepare your discussion post for the week, it's just going to be on hypothesis testing. So basically, just use your project idea to walk through the steps for hypothesis testing. Just sort of walk through and conceptualize what would occur at steps 1 through 5 using any research idea that interests you. You can basically lean on your worksheet to create these, that's fine. But just make sure to post your discussion by Friday evening on the topic of hypothesis testing. Oh God, this is always the worst lecture of the semester, and I just had to do this sitting alone in my bedroom, and I am thankful to be done. And as a reward for me, mostly, here's a picture of my dog back when she got a haircut several months ago. Oh, it was a wonderful time. All right, that does it for this lecture. It was a slog. I swear most lectures are not going to be this theory heavy, but I think this is pretty important stuff to get under your belt because it applies to everything we do from here on out. And with that being said, I'm going to stop for the day because I'm exhausted. All right, I hope you're doing well. Bye.